Okay guys, let's go now for the first part of lesson 6, which is titled Regression with Time Series Data, Spurious Correlation and Data Transformations. In the index, we will provide an introduction in which we will explain the reason why regression with time series is different from other types of regression. Second, we will present a specific problem, which is called spurious correlation. Later, we will discuss how transforming the data in the regression model can help us to detect whether a correlation is spurious or not. And last, we will provide a summary for the main points in this lesson. First of all, let's discuss the difference between time series and other types of samples. The distinguishing feature of a time series is that each value corresponds to a single date. Therefore, the values are dated and they are sorted according to the dates, so that the sample has a natural and unique order, from past to future. This fact determines which relationships are possible and which are not. Consider, for example, a sample relating age and height for a sample of individuals. In this case, the time in which the sample was collected is irrelevant. It will be the same if we collect the sample today or tomorrow or next week. We can even combine samples collected in different time points. Second, the sample can be sorted in different ways. We can sort it according to age, from younger to older, according to height, from taller to shorter, or in any other way that we want. Third, given any sorting criterion, age or height of an individual does not depend on the values corresponding to the individuals which are adjacent in that order. Fourth, causality relationships may be known. In this case, age typically causes height, or not, but there is no empirical method to assess the direction of causality. On the other hand, if we move to a time series framework, we can consider, for example, a time series of sales and advertising for a firm. The data may be quarterly, may be monthly, may be weekly, or whichever. In this case, the natural order for the sample is chronological. Second, current sales are probably correlated with past sales, while the other affirmation would be absurd. Current sales are not correlated with future sales, because there is no causality possible in that direction. Third, current sales may depend on both current and previous advertising. And fourth, there is a notion of causality. Series X grain share causes series Y if past values of X help to predict current values of Y. In this example, we could say that advertising is causing sales when past values of advertising predict current values of sales. Now we will discuss the statistical features of time series. Most economic time series take two forms, which have typical stylized features. First of all, there are low-frequency time series. With low frequency, we refer to the fact that these time series are sparsely collected. So we are speaking about monthly, quarterly, or annual data. In this case, we have here, from the 50s to the 60s, the time series of international airline passengers all over the world. This is a monthly time series measured in thousands of passengers. In this case, the time series displays, first of all, a trend. A trend means that the time series tend to move up. Second, seasonality. This means that the time series has a mean which changes over the year. And third, the time series has a variability which increases with the mean. In the other panel, we have the daily percent yield of IBEX 35. In this case, it is a high-frequency financial series. It is daily, so you typically have one data point per day in which the market is open. This time series has a stable mean, it has no seasonality, and it has periods of high and low volatility. So this is a cluster of high volatility, this would be a cluster of low volatility, another cluster of high volatility, and so on. Therefore, when we are working with time series, there are some statistics that typically we cannot take for granted. For example, the mean. In this case, the mean of this time series is either undefined or changes over time. It goes up. The mean in this time series also changes because the time series has a seasonal fluctuation over the year. So the mean in a given month, for example, in August, will be different from the mean in January. And also, the time series typically have unstable variances. In this case, this variability takes this form. In the other case, it takes another different form. Now, let us discuss our agenda. We'll concentrate in time series of the first type, that is, low-frequency time series. Bearing in mind its stylized features, that is, trend, seasonality, variability, and whatever, the main points will be, first of all, that there is the risk of creating a spurious correlation when we are relating variables of this type. A spurious correlation is an apparent relationship between two variables with no logical connection. Second, we will learn how to avoid this risk by an adequate treatment of the variables in the model. There are three main approaches that we can use to this end. First, transforming the data to induce in it good properties such as a stable mean and a stable variance. Second, adding regressors which are co-integrated with the endogenous variable. Third, adding to the model deterministic regressors designed to capture the trend and seasonality of the endogenous variable. And last, we will learn how to detect and model possible autocorrelation in the errors of the model. Now, let's present the problem of a spurious correlation. As I have just said, a spurious correlation is an empirical relationship between two variables with no logical connection. It may arise both when we are modeling cross-section and time series data. For example, in 1952, Niemann showed that the relationship between the number of birds and the population of storks, stork is cigüeña in Spanish, in several regions was significant, and he found a high correlation between both variables. On the other hand, Joule showed with English data that there was an important correlation, 0.95, between the rates of mortality and ecclesiastic marriages in England. Therefore, spurious correlation may appear in any framework, but it is more common when we are relating trending time series. The question here is how can we distinguish between true and spurious relationships? I will also show now an example of a spurious correlation and how to detect it. The figures show the annual series of US GMP, which is the thick line, and melanoma incidence in the male population of Connecticut, with the data adjusted for age, which is the thin line. Here you have the time series plot. Here you have the scatter plot. It shows a nice linear relationship. This dataset is available in the virtual campus with this name, GDP versus melanoma EN. Prima facie, both series seem to have a strong relationship, but it is absurd. The reason why they seem to be related is that both are trending. So when you are relating trending time series, you have to be very careful. Okay, so with this data, if we adjust a linear regression with a dependent variable GDP and a planetary variable melanoma incidence with a constant term, you will get important coefficients. They happen to be similar, but there is no reason for this, with a very small standard error, yielding a strong and significant relationship, with an R squared of 87%, close to this value. And this is the graphical representation of this relationship. So, if we believe that this model is correct, that would imply that an additional case of melanoma within the male population of Connecticut adjusted by age, this would increase expected GDP in this amount, which is a bundle. So now let's address the key question. How can we distinguish statistically between a spurious and a non-spurious relationship? Assume that this relationship that we considered in previous model was valid. So MT, the number of cases of melanoma, is causing GMP sub T. If we move backwards in time this expression, we would get GMP sub T minus 1 equal beta 0 plus beta 1 M sub T minus 1 plus epsilon sub T minus 1. Subtracting both equations, we will have this guy here. That is, a relationship between the increase in GMP and the increase in the number of cases of melanoma, with the same slope parameter. So now let's try to estimate this model. dGMP is how Gretel calls the first order difference of GMP, and d melanoma will accordingly be the first order difference of the variable melanoma. In this case, this parameter is not even close to the one that we saw in the previous listing. It is non-significant, and the XY plot between the both variables after differencing shows that they are not related. So, in the previous model, the apparent relationship was caused by the trend. If we adjust for the trend, for example, by differencing, then the relationship disappears. And this is a good test to detect spurious correlations in time series. Now let's speak about data transformations. As we will see, transforming the data in the regression model is useful to stabilize the variability of the data, also to adjust for any trend that the data may have, and also to adjust for seasonality. A common approach to avoid spurious correlation when modeling time series data consists in building models with variables transformed to induce stability in the mean and stability in the variance. A time series with a constant mean is called stationary in the mean stationary, or just stationary. On the other hand, a time series is homoscedastic, stationary in variance, or variance stationary, when it is stationary in the mean and presents a constant dispersion with respect to the mean level. Note that if the mean is not stable, the variance is not defined, as the variance is the average of squared deviations from the mean. In this section, we will introduce a data transformation, which sometimes stabilizes the variability of the data. Second, a family of transformations, which are variations of the differencing that we saw before, which stabilizes changes in the mean due to trends and to seasonality, as well as an interpretation for the variables resulting from common combinations of these transformations. So, let's see some examples with real data. First of all, the annual level of rain in the Midwest. This time series is stationary in the mean, because its mean level is more or less constant over the sample, and we can also see that the dispersion is more or less stable, so it could also be homoscedastic. On the other hand, the industrial production index in Spain shows a trend which is not stable. As you can see, the time series moves up and down. It also has a change in the mean due to the seasonal variation. During the months of July and August, industrial production falls sharply, and you can also see that the variability of the time series around here is smaller than the variability around here. So this time series displays all the features which are standard in low frequency observed time series, which are trend, seasonality, and a variability which depends on the level. Then here we have the monthly return of railway bonds in the United States. As you can see, this time series displays changes in the mean. The mean is more or less stable around here, but here moves up, falls down, goes up, goes down. So it is not stationary in the mean. Last, we have here the seasonally adjusted US civil unemployment rate. This time series has properties which are similar to the previous one. It has no seasonality because seasonality has been erased from the data to make it more comparable, and it has changes in the mean. So let's talk now about how can we detect that the variability of a time series is changing over time. The first and simpler tool is a time series plot. Here we have the time series of airline passengers, and as you see, as time goes by, the variability in each season tends to go up. So in this case, we can say that the variability increases when the mean increases, because this time series also has a trend and also has seasonality. Another alternative tool to detect this pattern of variability changing over time is the range mean plot. Here we have the range mean plot for this time series. Each data point is the mean for 12 months and the corresponding range. The range is defined as the difference between the largest and the smallest observation in each subsample. As you can see, when the mean goes up, that is, when the time series moves up, the variability measured by the range also moves up. So Gretel kindly adjusted a regression line showing that the pattern between mean and variability is more or less linear. This type of change in the variability is often corrected by the log transformation. So if the original data is y sub t, we will work with zt, which is the log of yt. Log stands for the Neperian log. This transformation also has other advantages that we have seen, as it induces normality in the sample and linearity in the relationships. Note that the transformed series that we see here is not homoscedastic stricto sensu, because the mean remains unstable, so the variance is not defined, but the variability is more or less stable and independent of the level of the series. This transformation works in this way because of the shape of the log function that you see here. The log function is such that if we transform by logs two observations which are very large in the original metrics, the log transform have a smaller difference. And this is the reason why the small variability observations around here have now a more comparable metrics with the large variability observations that we had here before the transformation. Okay, so we know now how to stabilize for changes in the variability. Now we want to stabilize the mean. The first idea that we can recover from the example of a spurious correlation is to apply a regular difference to the data. If the original data is yt and we logged it to make homogeneous the variability, the first order difference of yt will be zt, equal to log yt minus log yt minus 1. From here on, I will reserve the letter yt to denote the original time series, and zt the value of the time series that I get after applying a transformation. This transformation is so common that I will denote it by nabla. So nabla log yt stands for the difference between log yt minus the previous value. And this is the result of applying this transformation to the airline passengers that we saw. As you can see, this transformation is useful to adjust for the trend of the data. But we also see that this transformed variable displays some systematic variations around the mean. These systematic variations are due to the seasonality of the time series. So we not only need to adjust for the trend, but we also need to adjust for seasonality. And we can do this by using the seasonal difference. The seasonal difference of yt is defined as log yt minus log yt minus s equal to nabla sub s log yt. S in this case will be 12. It is the number of observations per seasonal period. So if the time series is monthly, like in this case, S is equal to 12 because we have 12 observations per year. If the observations were quarterly, okay, we would have 4 quarters per year, so S would be equal to 4. Note that this transformation eliminates the seasonal fluctuation, but the mean remains unstable. Okay, so if we know how to stabilize the variability, and we know how to stabilize the trend, and we know how to stabilize the seasonality, what we can do now is apply the 3 transformations one after the other. So if the original data is YT, we log it, we apply the seasonal differencing, and we apply the regular differencing. And this will be a time series which hopefully is stable in the mean and also in the variance. This is the result of applying this transformation to the airline passenger data. It is clearly stable in the mean. It doesn't display seasonal fluctuations. Perhaps the variability here is not the same of around here, but remember that we need homoscedasticity in the residuals, not in the original data. So with this mental note in mind, okay, we can proceed now to model this time series. The previous transformations may be statistically useful, but they are not intuitive. So it would be nice to have an intuitive interpretation for them. Consider, for example, that the original data is yt, and we compute log yt minus log yt minus 1. This is the time series that we are going to interpret. And it can be also denoted as nabla log yt. Okay, so zt can be defined in this way or can be multiplied by 100. Now you will understand why I do that. So I am working with this time series or I am working with this time series. Let's stick to the first one. If zt is log yt minus log yt minus 1, it will also be equal to log the ratio of yt divided by yt minus 1. Yt divided by yt minus 1 is 1 plus p sub t divided by 100, where p sub t is the percent growth rate of yt when moving from t minus 1 to t. And it can be immediately seen that this value, log of 1 plus pt divided by 100, is approximately equal to pt divided by 100. So the first transformation can be defined as the log rate of growth of yt in unit metrics, that is in tanto por uno in Spanish. We would call that tanto por uno. If we multiply this transformation by 100, we will have here the log growth rate of yt in tanto por ciento, that is in percent terms. So this transformation can be interpreted as an approximation to the standard percent growth. Let's see an example. We have t equal to 1, 2, 3. Yt is equal to 100, 101, 103. I've chosen these values to show that the growth rate from t equal 1 to t equal 2 is 1%, and the growth rate from t equal 2 to t equal 3 is 2%. Now the natural logs of yt are these values. And if I compute log yt minus log yt minus 1 multiplied by 100 to make the values comparable with the percent increase, we see that the first value is very close to 1% and the second value is very close to 2%. So we can understand these values here as an approximation of the standard growth rate. And we can also interpret these values here as a different rate of growth, the logarithmic rate of growth. Now let us review the interpretation of the transformed data in some common cases. First of all, if you have zt equal log yt, you are out of luck because this time series, zt, has no interpretation other than it is the natural log of yt. Second, if we have ct equal to yt, note that it is without a log, minus yt minus 1, this will be equal to nabla yt. This will be the change in yt, and it is an indicator of absolute growth, that is, the growth of the time series in the original metric. If ct is equal to log yt minus log yt minus 1, or nabla yt, or alternatively, it is the same transformation but multiplied by 100, this would be the logarithmic growth rate or log growth rate. This is an indicator of relative growth. When multiplied by 100, it is an approximation to the standard percent rate of growth. Now consider the following mess. Wt is log yt minus log yt minus 1, so nabla log yt. But you apply again a difference. So ct is wt minus wt minus 1, which is the first order difference of wt or the second order difference of log yt. So what you are doing is computing the logarithmic growth rate and subtracting the current value to the previous one. This will be therefore the change in the log growth rate. It would be an indicator of acceleration in relative growth. Imagine, for example, that Wt moves from 1% log growth rate to 2% log growth rate in the next period. So from 1% to 2%. 2% minus 1% would be 1 percentage point. So you could say that when moving from 1% to 2%, your growth rate have accelerated in 1 percentage point. So the difference of a growth rate is an indicator of acceleration. Now let's go for the seasonal differencing. As we saw, zt is defined as log yt minus log the value of yt in the previous season. So nabla sub s log yt. This can be interpreted as the growth rate accumulated over a complete seasonal cycle of s periods. When the seasonal period is a year, it is often described as the annual growth of rate. Last, what happens when we compute the annual growth rate, nabla sub s log yt, and we subtract the current value minus the previous one. So the transformation in the nabla notation would be nabla sub s log yt, which what we will have here is the change in the growth rate accumulated over a seasonal cycle, and it would be an indicator of acceleration in the annual or accumulative growth. Imagine, for example, that Wt is inflation. So we are comparing the consumer price index in the current period with the same value in 1 year ago, both in log terms. What we would have here would be the log inflation rate. And then we compute the current inflation rate minus the inflation rate that we had 1 month ago. If we move from an inflation of 3 points to an inflation of 3.5 points, we could say that the inflation accelerated its growth by 1/2 percentage points. Conversely, if we move from 3% inflation in log terms to 2.5 inflation in log terms, then we will have observed a deceleration of inflation by 1/2 of percentage point. Now I will provide some highlights for this lesson, which is especially important. So I will review them one by one. First of all, the defining feature of a time series versus other types of data, for example cross-section, is that the sample has a unique and natural order from past to future. This fact determines which relationships are possible and which are not. For example, it is possible that the current value of a variable is related with its past values. It is also possible that the current value of a variable is related with current and past values of other variables. Economic time series have typical properties. They typically are heteroscedastic and often show trending behavior and seasonality, which are two different types of non-stationarity in the mean. When the time series is non-stationary in the mean, there is a risk of creating a spurious correlation if we relate this non-stationary time series with another non-stationary time series. To avoid spurious correlation, we need a treatment for non-stationarity. In this lesson, we saw that we can do this by transforming the data to induce stable variability and also a stable mean. In the next lesson, we will see that we can also do this by including in the model explanatory variables that are co-integrated with the endogenous variable, and they capture the trending behavior. Or we can also do this by including in the model deterministic explanatory variables that we define, and they are able to capture trending and seasonal non-stationarity. So that is all that I wanted to explain to you today. Good night and good luck.